Hey, hi all. Good morning. Welcome to the session.
Hi, good morning.
Good morning,
Yeah,
sir.
yeah. So I see some of the students are from IITM campus, so they are making a joining request to the meet. Uh, yeah. Uh, Manoj Kumar, are you from IITM campus student? Are you an IITM campus student? Okay, okay. Okay, so let me share the presentation. Give me a second.
Sir, just to check, this session is getting recorded, right?
Yeah, it is being recorded and also being live streamed in the YouTube. So last time there was a problem, in the sense the streaming happened in the Google Meet.
Yes, we saw the discourse.
Yeah. So anyhow, I'm for safety, I'm recording the meeting. So at least if there is a problem with YouTube streaming, then we can use this. But I hope this is being streamed in the YouTube channel as well. Okay. Yeah, are you able to see the presentation?
Yeah,
Yes.
Okay, so let me wait for a couple of minutes because typically people join 5 to 6 minutes later. And also, how many of you have joined the previous session? Because I discussed, I followed a new notation, not new notation, new dimension, and discussed a few things. Is there anyone who didn't join the previous session that happened on Friday?
I couldn't find the link. I didn't find that in the calendar also.
Yeah, I mean,
Same here.
yes, you didn't join the session, but the video, the streaming link or neither the session was recorded. So
Yeah, and also I am not able to access the link that was provided in the instruction section link in the portal. So there was also the link is not updated, and I'm not accessible. I'm not able to access that.
okay, so the link contains wh- where does that lead to? The link for the videos or an assignment, sir?
Yeah, it is in last session it was provided that all this link for all the live session was provided in the Excel sheet in a
Okay,
Google Doc
okay, okay,
sheet. But now I'm not able to access that,
okay,
so
okay.
I
So,
could not join.
mhm. Okay, fine. Yeah. So anyhow, I discussed about especially the covariance matrix and then the kernel matrix. So I try to keep. So I reserved this kernel PCA concept for this session because it takes time to explain both covariance matrix and then gram matrix and then kernel PCA. So today I try to keep, try to teach the kernel PCA independent of things that is being covered in the previous session. But I hope you all have watched the lectures of week 2 and week 1. Um,
Yeah,
is, is there
yeah.
anyone who is yet to watch week 2 lecture, especially that kernel PCA stuff? I hope all of you have watched. Okay, so before moving on to the session, I just would like to know, what are your doubts in kernel PC? Of course, the content is dense in the sense there are a lot of concepts involved in week 2 lecture. So you have to, you know, put a lot of effort to understand things clearly to get a good grip on this concept of kernel PCA and kernel function. You have to put a lot of effort. So you may have queries and you may have doubts. If you, if you all ask your doubts now, I keep that in mind. So when I cover this uh, lecture, right, in this session, I try to address them along with the presentation. So I have something in mind. So I try to reinforce the same ideas covered in week 2 in a different way by giving some illustrations and making it clear as much as possible. If you come forward and tell your doubts where you are having the difficulty, I try to address them along the way. How many of you are 100% confident that you got the concept of kernel PCA and its working principle, everything. Okay, so the rest are having some doubts. Okay, so in the last session also, many students said that they were not able to grasp the week 2 contents. I mean, it's some sort of missing pieces. Okay, so I quickly go through the slides. I mean, the things that we have already discussed in the previous session, not elaborating much. Okay, so the one thing that if you haven't attended the previous session, what I am following in the presentation is I am keeping the matrix X, which is the data matrix or a data set, where I use the rows to denote the samples. Okay, so the first dimension n is in fact okay, so this is number of samples that we collected, and d is number of features. Okay, so just to I am taking this approach just to what to say, so you can see how things works if I change switch the dimension. Okay, so the concepts remain same, but only the calculations might differ a bit. Okay, and this is very important. Okay, so because of this, usually what happens is wherever you see x transpose x, it will be switched as x into x transpose. That is the change. But keep this in mind whenever I use x, I mean whenever I refer to the data set x, so I am referring, and the dimension of the data set is n by d. N is number of samples and d is number of features. Okay. Okay, so in the last session we discussed about we took a simple example and discussed about what covariance is and why we need to do this mean centering. Is it essential, or can we do can we compute the principal components without doing mean centering? All these things we discussed in the previous session. Okay, and in fact we looked into the structure of the covariance matrix, and then we try to make sense what each element in the covariance matrix actually denotes. Especially we try to we make sense that the diagonal elements of the covariance matrix is actually computing the variance of each feature. Okay, so for example x11, sorry, not here, in C. Okay, so if I compute the covariance, then I'm ending up with 4 elements. Okay, of course, again I didn't fix the mistake, so it should be C11 something. Okay, so it's the elements of the matrix capital, this should be C. Okay, so each element actually represents the covariance. The diagonal is actually the variance of the features. Okay, so if I have d features, then the dimension of C is going to be d by d, and the
So
diagonal
it would be X transpose, right? Matrix.
Yeah, that is true if I followed the dimension as mentioned in the lecture, right? So it should be x transpose x in this case. If I kept x as d by n, okay, then x into x transpose makes sense.
Sir, I have a doubt here. So, suppose we are setting it as n into d, then why can't we use x into x transpose only?
Give me a second. Many people are requesting to join. Give me a second. 1 second, please. Okay, so what's your question? Could you repeat that?
Sorry, I was on mute. So I was saying that even if we selected as the our x as n into d, right? So
Okay.
why can't we just stick with the original formula as x into x transpose for
No,
covariance?
that won't compute the variance. That's what I'm saying, right? So if I say, for example, here you are seeing these elements C11 and C21. So how do you compute C11? Okay, so what is C11 actually? You take the first row of x transpose and multiply with the first column of x, right?
Mm-hmm.
So if you do so, what you are ending up with is this one, x11 square, x21 square, and here in the diagonal x12 square, x22 square. So what this summation actually denotes, so I am squaring the remember the first index in x11, this one denotes the sample number. Okay, the first index denotes sample number, and this one denotes the future number.
First feature.
Okay, so what I'm doing is I'm taking the first feature of sample 1, squaring it, and then taking the first feature from sample 2 and squaring it, right? This is actually, we are of course we have this 1 by n term here. This is actually variance, sample variance. Okay, if I change the order x into x transpose, you won't get this. Okay, that doesn't denote the variance of the features, neither the variance of the features along the diagonals nor the covariance in the off diagonal elements.
Okay. So just because we want that this should be the variance, so we are sticking with this x transpose x. Yeah.
Yeah, always remember that when you compute the covariance matrix, the output dimension should be of size d by d, because we are
Okay.
computing the variance of the
The
features.
D denotes the number of features, so we have to stick with this only. Okay.
Yeah. Okay. Okay, so that is what the covariance does, and we discussed about what is the covariance matrix for this particular example with 20 data points, and then we made sense of these numbers in the previous session. Okay, so where the variance is, even in the covariance matrix, gives us some idea that how the data set is spread in the original input space. But we wanted to decorrelate the features for various reasons, so that's where we are going with this principal component analysis. There are multiple ways you can derive the principal component analysis, from posting this as reducing or minimizing this reconstruction error, or posting this as kind of decorrelate the features. Okay, so yeah, so I hope now all of you have at least some idea about what the principal component is, and how the eigenvector denotes an eigenvector and eigenvalue denotes the principal directions. Okay, and where the eigenvalue denotes the variance. Okay, so these things I discussed in the previous session, but let's quickly skip this. One other way of see, I'm using this x transpose x. What if I use x into x transpose? Both are symmetric matrix, right? So one advantage, as mentioned in the lecture or in general, is that especially when you have number of features that is much greater than number of samples, then the dimension of C will be really big. So we want to reduce the computation, so we switch to the other approach. Okay, I mean, I just change the order and compute k. Okay, so from k I try to once I have k, so in this example, right, here k size is 4 by 4, whereas C size is 10 by 10. So instead of computing the eigenvector and eigenvalues of C, we compute the eigenvectors and eigenvalues of k, and we try to relate. Okay, so we map these eigenvectors and eigenvalues to eigenvectors and eigenvalues of C. Okay, so it is viewed from the perspective of reducing the time complexity or computational complexity. Okay, and we discussed all these things, and I hope you are comfortable with this, how we transform.
What is K? I mean, I have seen I've seen this. This is a formula, or I mean, this is given in the. I understood this x into x bar, but what does this mean? K.
So now you simply view K as a symmetric matrix and also positive semi-definite matrix. It is not doing any other thing. Okay, you can't say, like in the case of C, each element denotes the variance and covariance, but K, we don't have such interpretation. We simply say it is a dot product between the elements of X.
Okay.
You can think of as it represents some sort of similarity between the features, but we don't need to get into that in order to understand the concepts. I mean, what this K is, how this K is actually useful.
Sir, in this case, if suppose we had D into N, so we need to take K as x transpose dot x.
Yeah, that's what. So wherever, see in the lecture, wherever you see x transpose x, the moment I switch the dimension of x to n by d, simply the order changes.
Okay, thank you, sir.
I
Sir,
did this just to to give you a feel that when we change the dimension, how things works. Okay, and especially when you are dealing with matrix, you should be very careful. That's what I'm trying to do by doing this.
Sir, Kij is Xi transpose Xj, right?
Yeah.
For each data X.
Yes, yes. For a particular element x in K, it is Xi and Xj transpose.
So, sir, here can we consider x11 square as the variance, sir? Because it's sum square of all the features in the first sample. So, can we consider that
That's
the
not
first?
the variance. I mean, if you have something like this, right?
Yes, sir.
I mean, this is what we want. Okay, so if this is the case, of course, we can say the first element of K11 denotes the variance. But for this product, the first element of K11 is computed like this.
Yes, sir.
This is not the variance of the feature, right? The first feature, because you are taking the feature 1 here, taking feature 2 here, you are taking feature 10 here. You are squaring the each features. So this is not
Okay.
the variance, right? Variance of a particular feature. It's a kind of, you are considering all the features. It is neither covariance nor the variance.
Okay, sir. Okay.
Okay, so now we know we have a way to switch back and forth between K and C. Okay, so we derived all these things in a different way. Either you can follow the lecture or you can follow this approach, doesn't matter. The key takeaway is, instead of computing the principal components by using C, I'm computing the eigenvectors of K, and then I use this to transform these eigenvectors to the vector space spanned by C, that is the principal components of C, by this relation. Okay, so this entire term
Sir, can you
is,
please show this relation with some numerical problems, sir, to understand it better?
the problem is that,
Conceptual wise, I can understand, sir, but when we are applying it into the problems, I'm stuck in this step, sir, actually.
okay, I would advise, because we can, I mean, if you want some sort of manual computation problems, right?
Yes, sir.
But we can't go beyond 3 by 3 if it is manual computation. What I would
Even
advise
2
is
features
that,
also is okay, sir. To understand it better, that's also.
yeah, so I have taken 20 samples with 2 features to illustrate all these idea, and then I have written the code. Okay, so you can
Okay.
see all the diagrams in this presentation are coming from this collab. Okay, so what I would advise is that, are you able to see this collab? I switched the tab.
Yes, sir. Yes,
And,
sir. Yes.
so you can see I have written the code and applied all the concepts. Okay, so you can, I would advise the same, you try to reproduce it. Okay, so which means if you want to ensure that you have understood the concept correctly, instead of referring to the articles and of course solving problems, some textbook problem is fine, but the best way is to write the code and then see how things works.
Okay.
That is the best way,
So where
Okay.
do we
at
get
least
this code from?
according to me.
Sir, where do we get this code from? I mean, is it uploaded in the?
No, it is not there. So I'm asking you to write the code.
Okay.
Maybe if after some point of time. So I encourage all of you to write the code on your own if you are comfortable with NumPy. So if you are not comfortable with NumPy, I will share the code after a week time. Okay, so I give you a time space so that you can try on your own. And if you're not able to do that, then I will share it in a week time. Just tag me in the discourse and remind me. I share the notebook. But it is not well organized. It is like you have to put some effort in order to understand what things are going on. Okay, so where I was, yeah, so the crucial or the key idea is that I compute the eigenvalues of K, which is a smaller dimension of size n by n. Okay, so here we assume that n is much less than d. Then I transform these eigenvalues to the eigenvector to the eigenvector of C. Okay, so Wk is actually is one of the eigenvectors of C. Okay, and the mapping happens through this data set matrix. Okay, So that is the idea. So we say this is a dual formulation, or from one view it reduces the time complexity. The other view is to see that the same problem is solved in different spaces, and there exists a mapping between these spaces. Okay, so you can think of like that as well. And also note that here the eigenvector is, the dimension of the eigenvector is n by 1, but in the space of C, the dimension of the eigenvector is in fact d by 1. So we need a mapping. So you can do that mapping through this X transpose. Of course, we derived all these things, but intuitively this relation makes sense. Okay. Okay, so I just skip all this. This is the observation. Okay, so we have two matrices now. Both are symmetric matrices. All the elements in these two matrices are in fact computed by simply taking dot products between elements in X, okay, or elements in the set X, okay, and therefore both the matrices are symmetric and also positive semi-definite. Okay, so of course we have different name for this matrix. In general, in a very general way, it is called as gram matrix. You can call C also a gram matrix. Okay, but now we stick with the names. We call C as covariance matrix and K as a kernel. Okay, for reasons that make sense later. Okay. Okay, so now the other aspect.
Hello. So only difference between C and K is in the dimension, isn't it? C is D cross D and K is M cross M. Yeah.
A difference in the sense, yeah, dimension is different, but the way elements are computed is same. This is just a dot product.
Yeah.
Sir, in K matrix, how do we compute the eigenvalue, sir? As like it is in covariance matrix, sir?
Yeah, now we have a matrix K, so you can simply view it as a matrix K, symmetric matrix K, and then you can apply the general procedure. Of course, not the textbook's procedure, because in textbook we compute the characteristic polynomial that works for 3 to 4, even 5 dimension. But when the matrix size becomes larger, we have a very efficient ways of approximating, computing all these eigenvalues and vectors using some approximations.
Okay, sir. So in the exams, we were not asked to be solve this eigenvalues, sir.
No, we won't ask you to compute the eigenvalues and eigenvectors because you already know how to do that in MLF. But you have to keep in mind the various relation exist between the eigenvectors and values of K and eigenvectors and values of C, and how things are connected. So we explore you from that perspective, not in terms of computing vectors and eigenvectors and eigenvalues.
Okay, sir.
We may ask you, see whether this is a proper eigenvector of the matrix C. So that is expected, right?
Yeah.
That you can quickly cross check whether this is a proper eigenvector or not.
Okay, sir.
Yeah. So the one part is that we try to reduce the computational complexity from O d cube to O n cube, where we assume that where it is the case that n is much smaller than d. Okay, so it reduces the computation drastically. So the other aspect is the important aspect that will be subsequently used in the later part of this course is to break down the relationship. Okay, so if my data points are not linearly correlated, or even not in if there is a nonlinear relationship between the data points, then how do I apply PCA? That is the concept. Okay, so again, to motivate this, I'm taking some illustrations that does not exactly reflect what is going on in the mathematical equations, but it captures the essential idea. Okay, so here you can see I have some data points. I'm just using different colors, but as if we are doing some sort of classification. So I hope you are all aware of what classifier is. I have some data points, and I want to, and for each data point we associate a label. Say for example, all these blue data points belongs to, let's say, class 1, and this data points belongs to class -1 or 0, whatever. Okay, just for convenience, we are doing this to understand why we need kernel PCA in the first place, apart from this compression perspective. Okay, so we can see that these data points are not linearly separable. I can't draw any line that separates these two data points, but obviously I can see that if I want to separate these two data points, the separating line is going to be a circle in this R2, right? So I need to draw a circle, then only this circle act as a boundary that separates these two data points. Okay, so of course I can do that, but what I want to do is, can we somehow find a linear relationship, okay, between these two data points, and then make use of a linear classifier or some sort of, the concept of PCA in the higher dimension. I can't do anything in R2 dimension. Okay, so I have to add additional axis, then only I can even think of doing all these things. Okay,
So what is the objective, sir?
Objective for what? I'm not your here for this specific case. The objective is to find a decision boundary that actually separates these two data points. It's like now you assume we are doing some sort of classification. Okay, so I go ahead with a few steps, that will, that will convey you all the essential concepts. So if you are not able to get that after even going through all these steps, then you may ask the questions. Okay. Okay, so now what we are going to do is, I'm in R2 and I want to move to the higher dimension. Okay, it could be R3, R4, R5, R6, or whatever, even infinite, such that my data points are, the data points are transformed in some way where I can apply PCA. Okay, so remember, PCA requires us to, requires the subspace to be a linear. Okay, let me just go ahead and I will explain all these things in the subsequent slides. Okay, so what we are trying to do is, we are trying to map this R2 space to R3 space, data points from the R2 space to R3 space. Okay, so we are doing some transformation. Okay, remember, each data point is, now my data set contains two features, x1 and x2, and all the data points have two components, x1 and x2. I make use of these two components, x1 and x2, and I apply some transformation. Okay, where the first element is x1 square, the second element is x2 square, and the third element is root 2 x1 x2. For now, you don't need to worry about where this particular transformation is coming from. You just take it for granted such transformation exists, and I am applying it. Okay. Okay, so what does this transformation actually do to these data points? So that's what we want to see. Okay, so now you can see that we are now moving to move the data points from R2 to R3, and we have some sort of separation. Okay, so of course I'm using a new name, U, V, and W, to denote the components of these data points in R3. And clearly we can see these two circles are separated, which means I can draw some hyperplane here, right? So I can draw a hyperplane that separates these two data points. Okay, so you can think of this hyperplane as some sort of a decision boundary in classification algorithms. So if you haven't heard about classification algorithms, that is fine. If you have at least a basic idea of classification algorithm, this should make sense. Okay, so this boundary act as a decision boundary. So whatever the points above this decision boundary belongs to one class, and below this decision boundary belongs to other class. You can think of like this. Okay, so the important thing is that my decision boundary is now is a linear function, okay, which is a hyperplane here. But if I want to draw the same decision boundary that separates these data points in R2, I can't do any linear, I can draw any linear function which are lines in R2, right? The decision is going to be only non-linear function, which is circle in this case. Okay. The other aspect is, of course, we moved the data points based on some relation, which I will explain later, that separates these data points in some way. Okay. The next thing is often we want to project it to the principal components in R3. Okay. And of course, you can see that I can project these data points in any planes. I have 3 planes here. I can project these data points in any planes. And if I choose to project this onto, so which plane do you prefer to project these data points so that they are separated? Let's say I have plane 1 here, plane 2 here, and plane 3 here. So I want to project the data points such that these 2 data points are well separated, and I can draw a line between them.
Plane 3.
Plane 3, right? So visually we can see that at least in this toy setting, plane 3 is reasonable. Of course, you can do some sort of projection in plane 1, but some points will get overlapped. And since this is 3D, we can clearly see that plane 3 is a better option. Okay. So what happens if I project it on the plane 3? So if you project this, remember now what I have done is I have computed a transformation, okay, pi x of I. Okay, I have just transformed all these data points to a higher dimension, and it does something to these data points, and we don't know the distribution, all these things, but we just imagine that it has transformed the data points. Okay. Now we need to project it. For projection, we need to carry out some operations, right? Typically, if I have x, a single data point, and if I want to project it onto an eigenvector, then I will project it onto the eigenvector by computing the dot product. Okay. And similarly, we need a way to represent this plane, but assume that we have a way to represent this plane using a span of eigenvectors. Okay. And once you project this, you can see this data points becomes line in the projected plane, and I can also the separating. Remember now this plane is R2. Okay, my original data points is in also R2. Okay, but the the subspace R2, because our original space is R3 and R2 is a subspace. So the subspace in the transformed or in the future space makes our data point which are non-linear in the input space but linear in the subspace of R3. Okay, so these are some technical words. If you are not comfortable with that, that's fine. So you can visually see, you just projected this. Now I can draw any line, okay, in this plane that could separate this data point. Even I can use these lines, I can find the principal components in this plane and then project these data points. Okay, all things I can do now. Okay, so this is an intuitive idea how things, what we actually want to do. Pictorially we are seeing things, but we want to do this for higher dimensions. No, we can't say best access. Here I am just picking up 3 dimensions because we can see things. Okay, there could be much better access, even R6. Okay, but here I am just taking this for illustrative purpose only.
And sir, we are separating the points that are in red and blue for just now for this U and V. But how we are finding out that this should be the best plane between them?
Yeah, that will be computed by the kernel matrix. Okay, so we don't need to bother about it. Anyhow, remember now we are doing all these calculations in the future space, that is transform domain. But in practice, we won't do that. In practice, we never compute all these things in the transform domain. We compute all these things only in the R2 domain. Okay, which no computation takes place in the transform domain. The thing is that often we don't know this. Okay, that's the idea. We don't know the mapping at all.
So mapping is done by the programming framework that we are using.
No, here we can see. For some polynomial of order some degree 3 or 4, we can see the mapping.
Yes,
But
sir.
in general, we don't know the mapping, so we don't care about these mappings after all. Okay, so that's what the kernel actually does. That maybe I talk about all these things in the subsequent slides. Please wait till then, and we may reserve these questions, you know, for the end of the session.
Okay, sir.
Sir, sir, basically, for to apply kernel, so do we need always two different kind of data set?
No,
Or
not
two
different
or
kind
more,
of data set.
two
I
or
don't.
more. Like you said that here we are having like orange one and blue one data set. These are two
No,
different.
no, these are all the same. These are all X. Okay, let's say this contain. I mean, this contains some 20 points. This contains some 20 points. So totally there are 40 points, right? So my X contains 40
Okay.
samples. That's all.
Okay,
Right?
so it's just that we cannot align it in one particular line. So we are thinking to do these things, transformation and everything.
Yeah. So the key. So I am. This is just acts as a motivating example.
Mm-hmm.
The idea is that I have a structure in R2. Okay,
Mm-hmm.
which has then this nonlinear relationship. We took circles so that illustrate this is the best way,
Mm-hmm.
but it could be any relation. So you might have see a data point something like this.
Mm-hmm.
Okay, so this is just nonlinear. So we are looking for a space where this becomes linear, where I can apply a linear PCA. That is the idea.
Okay, got it. Thank you.
So basically R2 and R3 as in original, they are non-linear. After transforming, R2 have the linear subspace in R3.
Yes, that's correct.
Okay, sir. Okay.
Sir, we are doing representation learning, right? Basically, we want to find a representative and coefficient.
Yeah, that's true. But this act as a motivation. Kernel PCA is applied in SVM that you will study later. That support vector machine, where this is extremely crucial step. So the best motivating example, the best way to introduce kernel PCA is to introduce this classification problem. Of course, here we are just talking about representation, but as a motivation, we can take this.
Because the original data, which is in R2, we need two vectors to represent it.
Yeah,
So we want to reduce it.
yeah, that is true. So when you do this compression, we do that. But yeah, so let me cover this, and because there are some 10 more slides which I talk about all these things in detail, and you keep your questions, reserve your questions until the end of the session. So if you have very specific question to the kernel and mapping all these things, then keep that for the end of the session. Now if you have question in these mappings, okay, you can ask. If you are able to make sense of the flow, that's fine. If you have any struggle in understanding these concepts, you can ask it. Okay, so yeah, so we call this as input space and we call this as future space. Of course, we need to look for a plane in the future place, but we won't do that in practice. But I'm just putting this as a question. Okay, we project it onto the plane because we are visually seeing here. Okay, so just to cross-check your understanding, I have taken this figure from the original authors who developed this kernel PCA and even all these kernel methods. Can you make sense of this again? This is in the classification setting, how the data points are mapped into R3. Okay, so here it is R2, here it is R3. And you are seeing, can you make sense of why these data points are grouped the way like this? And these data points are you just, I would say, there
Hello.
also, yeah.
Do we need to think about the mapping or transformation we require to map into like
No, I mean, we never go for and we never look for suitable mapping pi of x. Okay, so that is the central idea here. Okay, so because we are not going to often map this to a finite dimensional space, we map this to infinite dimensional space. We go with radial basis function where we don't even care about the phi of x. Yeah, Viraj.
So the mapping would be determined by the kernel that we are using, right? So it
Yeah,
means it basically depends on whatever kernel we choose, the mapping will be decided after that.
yeah, that is sure. I'm not talking about the kernel so far. Here I'm just telling you, assume the mapping exists and ensure how the data points are actually transformed. And
Okay.
so in these two pictures, can you think of, you have a circle here and not ellipse here, and then you have points within this circle, and you have points, that are close to this decision boundary, and whether this closeness is preserved during this transformation, and what this line actually represents, all these things. Okay, so that's what I ask you to make sense. Okay, say for example, one thing that I would say is that there are 1 point and 2 and 3 4 5 points that are near to this circle in the R2 domain. Okay, so these points are also, you can see, right, some points are very close to uh, the decision boundary in R2 subspace of R3. Okay, so the thing is, the thing that I want to convey is that there are some interesting relations. Of course, you may ask which is the best degree transformation, right? Here I am using R3 as since you already know what the kernel is, you picked up degree 2. Okay, so how do you ask whether degree 2 is better than degree 4, or degree 3 is or degree 6 is better than degree 2, or you can put any p that is contained in any integer, degree 100, degree 1000. That's where the problem comes in. So why not you make it to the infinite? Okay, that always works best. Okay, but anyhow the data is going to reside in R2 no matter whether you're going to R3 or R6. But going to the higher dimension does, uh, simply moving on to the higher dimension has any advantage or not? These are all the questions that we need to answer, but now uh, we are not going into that. Okay, so the first mathematical step that we are moving forward, that we have to guarantee that these data points lie in the linear subspace of higher dimension. Okay, so that's where in the lecture also Arun sir take this simple example. I am repeating the same and I am going to ask you the question. Okay, you do all this stuff, and then you now I decided with I'm going with R2 and then polynomial 2 transformation. Okay, and then I have this transformation mapping, and I have this u, and note that now the u is constant given a, b and r. Okay, so if any data points is coming from f1 f2, I use this for mapping. This one is fixed because this is function of a, b and r. Okay, it is not function of f1 and f2. So if this is the case, right, now I have two vectors, and then in the lecture we claimed that this dot product between the transformed data point and this vector is 0, so that we can say the data is residing in the linear space. How do we say like this? So how do I say my data is
From where
residing only in the,
you take this u, sir?
sorry?
From where you have taken this u, sir, the vector u?
Yeah, you look at the coefficients of this one. So where is the constant? 1. Okay, so I need a constant. The first place is a constant. So what are all the constant quantities here? So these are a square. Not necessarily 1, it is simply a constant. Okay,
Okay.
so you pick up all these constant here, and then you refer to what are all the coefficients of f1. So it is 1, all these things. Okay, just by coefficients of these monomials.
Okay, for f1 the coefficient is 1 and f2 is also 1. Then where do you get this 0, sir?
I don't have this one, right? F1 f2 in this.
So
Okay.
dot product of the transform feature and u should be equal to that f1 square plus a square minus 2 f1, that, so that it will be 0.
Yeah, that is okay, but I'm just focusing on this is a general equation, not only specific to this particular example. What we are claiming is that we have a data points that is being transformed, and we compute a dot product with some vector u corresponding to that dimension, and then it always result in 0. So there exists an equation like this which guarantees that the transformed data points live in a linear subspace. So why do we say it lives in a linear subspace with the help of this equation? And that's what in the lecture also, I mean, Arun sir mentions this in the lecture, right? He simply says now the data points are living in the linear subspace. The transformed data points are living in the linear subspace.
Sir, it is because maybe there exists some vector in the higher dimension which is perpendicular to all other transformed vectors.
Yeah. So the idea is same. So again, to make sense of this, we have to stick to R2 and R3 where we can visualize. Okay. So I pose this question. Let's take for example, u is fixed. Okay. And I want to project the transformer vector onto this u. So I can't change the u. And let's say u is fixed. And how many directions I have for this phi? Because this implies that since you fix this u, we need a vector that is always orthogonal to u. So how many directions we have now?
2.
Okay, so we have two directions, right? Either in this direction or in this direction. Okay. So if I go to R3, what happens? How many directions? Again in R3 we fix u. Then how many directions do I have for transformed space? 3,
4.
4.
Or how many vectors are there? Okay, how many perpendicular vectors are there in R3 for the vector u in R3?
Again, there is only, sir.
There can be infinite.
Yeah. So the answer is infinite, right? So what this actually says, the moment I go to R3, things becomes like this. Okay, so let's say this one represents the vector u. So the entire plane, right, that is spanned by some um, some basis. Okay, so we don't care. But what I can see that is that whatever the vector I draw in this plane in any direction I wish, this is going to be perpendicular to u. That satisfies this equation. Okay, which means it simply implies that my transformed data points reside in these planes only. I don't know the shape, but whatever I do, it is going to reside in this plane. So it is going to live in a linear subspace. Um, um, that is the key idea. Okay, but remember we don't know the shape. Originally I have circular, I can have any shape in my input space domain, but the moment I transform, it is going to live in a linear subspace, but I don't know how the data points are distributed. And okay, but once again we don't need to care that, but the important concept is this, and the important equation is this. Could you make sense of this one now? Why it is called as linear subspace? Why the transformed data lives in a linear subspace? This holds true for any dimension. Okay, so if you go to R5, then I will have a hyperplane, okay, which is spanned by 4 eigenvector, any vectors, and basis vector. Okay, so I hope this is clear now. So keeping this in mind, now we are having so many dimensions. Okay. Yeah, our objective is to find the principal components in the transformed subspace and do the projection, all these things. But I come back to this later. That now I want to focus on these dimensions. Okay, so my original data contains n samples, each of each contains d futures, and then my transformed data is going to have the same n samples. Focus on that. We can't change the number of samples. Only thing is that we can change the number of features by doing this transformation. Okay, and always d is always much greater than d in typical or in a practical scenarios. Okay. Yeah, Raj.
So the polynomial kernel, we have to choose a p. So say for example, we take a very, very high p. Then sir, does that somehow risk overfitting?
Yeah, that is with respect to the classifier. Yes, overfitting does happen, so that will be discussed in the classification algorithm, I hope.
Okay.
Sir, here, like you said that we are in like D, capital D is the number of feature. How we are saying that, like suppose we had 10 features or 100 samples, and then we are transforming it, whatever, doing the projection and all. Then how we are saying that we are increasing the features, because features will be same, right? We are
No,
just projecting it into another plane where it has to be linear.
yeah, then my features changes. See, I have x1 and x2, which are two features. Okay, then I transform this into x1 square, x2 square, and product of x1 and x2, right? A square root 2 term is there, but these are all the terms involved. So now my x1 square is a new feature, transformed feature. Let's say I call this as u, and this one v, and this one's w. So originally I have two features, and in the transformed space I have three features. Of these two are correlated because it is constructed out of the product of x1 and x2. The features becomes correlated, but the number of features increases, right, because of this transformation.
Because we are increasing the this dimension space, we are increasing another this because of that.
Yeah, that is true. See, you can plug in a practical scenario. It could be age, it could be height, and the product of age and height might denote something, right?
Mm-hmm.
So I can think of this as a new feature, but a correlated one.
Okay.
Okay, so which means the objective, the right now the current objective is to find the principal component in the transformed space, which we can do by using the covariance matrix in the transformed space, which that is exactly similar to how we compute covariance in the input space. Okay, we just simply take this product in the transformed space. Okay, so this makes sense. So how should we compute all these covariance matrix, or do we need to compute this, and what are all the problems with computing this covariance matrix? That is the next topic. Okay, and now you see there are three dimensions involved, n, d, and h. We know all these things, and I'm not sure if this one is used in the lecture, but typically we use this, instead of r, we put this here. The features are in r, but in the transform domain, the feature could be infinite, which is generally called as Hilbert space, and you don't need to know that, but I'm just highlighting this here. Okay, so now we have different cases. One is in the original input space, my number of samples are much greater than number of features. Then I can compute the covariance matrix using this product, and then find all these eigen values and vectors. Okay, and you look at how many dot products are being computed. Okay, and the other case is this. That's where we talk about this kernel matrix K. Okay, so instead of using x transpose x, we use xx transpose. And I'm stressing this: do not stick with this pattern. Whether it should be xx transpose or x transpose x is based on how we represent x. Okay, so now we have a case. We are introducing a new dimension d, and it is true that d is always much greater than n, and it is also true that d is always much greater than d in the real world. Okay, so theoretically you can argue there exists for some small cases you can invalidate these claims, but in practice this is the case. Okay, d is always going to be greater than n and also greater than d. Now we are facing a problem. Okay, so if either of these inequality is not true, then we can go with C or K. Okay, but both inequalities are going to be true in the real world. So One thing is I can compute the covariance matrix, okay, or I can compute the kernel matrix in the transformed space, okay. But either way, this is going to take a lot of computation, okay, because this is a point I'm repeating this. We never compute this phi of x directly, okay. We don't want to compute that. So unless we have this phi of x, we can't compute this c, but we can't compute this k. But we use these equations just to make correlation with the previous steps, okay. Just give me a second. Yeah, I will. Okay, so are you able to follow up, follow with me? So I'm making a lot of claims. Can you make sense of this, or does this make sense to you? Okay.
Yes, sir.
Okay, so let me take a simple example to see why d is always much greater than n, and also much greater than small d. Okay, so let's take this simple example, which is from the original paper. Let's say I have an image of size 32 by 32. It's a very small image. Okay, it's a very tiny image. 32 by 32 is, in fact, if you capture an image in your mobile, it will be of size 1000 by 1000. Okay, so this 32 by 32 is a very tiny image, and I want to apply this PCA to this to this image, and I can see that these are all not going to be linear, so I am doing some transformation. I just want to apply a polynomial transformation of order 4. Then I want to see what would be the dimension in the transformed space. Okay, so in the transformed space, you can see that it reach the dimension in order of 10. Okay, you just apply this formula and you just forget about this. It is in order of 10. Let's say it is 1 to the 10 to the power 10. Okay, which means my d is now greater than billion, right? But what is n? N is number of sample. Nowhere you collect number of samples that is greater than 1 billion. Okay, even in today's deep learning setting, in deep learning setting, it can go beyond 1 billion, especially it's for companies like Google, that's possible. But typically, having 1 billion samples is not feasible. It is not even 1 billion, it is around 4.5 billion for this simple transformation. Okay, and it is clearly much greater than d, and you can see the difficulty.
Sir, what is 1028? Is it d?
It is just I'm converting this image to a vector. We have samples as a vectors, right? Now I have an image which is a matrix. I'm just flattening this matrix into a vector.
So this is basically the formula by d plus b, d plus p, c, p. That's one, no, sir. In that way, you have converted.
Which formula? D plus
P, the polynomial power.
yeah.
Dimension plus
Yes,
polynomial power.
Yes, that's correct.
Okay.
So we see the problem, right? So I mean the enormity of the intensity of the problem. It's in practice, this is this setting. Okay, so we can see there is no way out.
Sir, that should be 32 square, sir. So 1024.
Is that the case? Yeah, 1024, but
1024 plus 4. Yes, sir. Correct. 1028 is correct, sir.
Yeah. Okay, so now we can see the intensity of the problem. Just imagine that these techniques, PCA, kernel PCA, were proposed in the year 1960 and even in 1990, even revisited in 2000. Okay, where the compute resource is very, I mean, the computer was just under development, and collecting even thousands of samples is not easy, even for a simple task like collecting digits of an image, right? So we can see the problem, even it is a problem today as well. Okay, so how do we tackle this problem? One thing is, even if I want to apply this transformation, even computing one single phi of xi, okay, see how many products I need to compute. Okay, So that soon I will run out of memory. I can't even even storing a data set becomes a problem. Okay, so this is one important takeaway. We never ever compute this. Okay, this is bad idea. We never ever compute this phi of x. We keep this in the derivation for manipulation to work around this, but we never compute this. Okay, keep this in mind. Okay, oftentimes it is invisible. So, and let's try to connect so many dots here. So one is I have a data set X. Okay, so I'm using MathCalc just to denote this general set. We know that it is a lower dimensional input space. Okay, so dimension is the number of features. Okay, then I apply a transformation. The transformation could be anything. It could be but for simplicity, we say it's a polynomial transformation. Then it maps these data points to a future space. Okay, which we called as future space, but in generally it's a Hilbert space because the higher dimension could go or could include this infinite as well. Okay, so what are all the steps? Our objective is now to find these principal components and in the higher dimensional space phi of x domain. Okay, but we know that computing phi of x itself is infeasible in many settings. Okay, so yeah, computing a single transforming a single data it's itself infeasible, and doing some operation between this data is also infeasible. Okay, but to compute the covariance matrix, I need to carry out these operations. Okay, so because we are doing all these things in the transform domain. Okay, so what is the way? So we see that the Hilbert space or the future space is not suitable to carry out all these things from the practical standpoint. So what we do is, why not we make the computation equivalent? Okay, so whatever the operations I carry out some operation and it gives us some numbers as an output, and I want to induce the operation in the lower domain and the lower dimensional space. Okay, that we have already seen how to do that when we talk about this K and C. Okay, that is there also in the concept of dual formulation. There also we switch between C and K, where C is higher dimension and K is lower dimension. So it is possible. So we can do that. Okay, so a kernel function exactly does that. So what kernel function actually does? So we have this sets. Okay, so for all the combination of pairs from this set, we apply a function. Okay, so it could be any function. Here we use a dot product, and then okay, you take an element from this X. Okay, not from this H. Okay, so the elements are from X, and then we do something and it returns. Of course, this is a scalar. Okay, and this scalar is equivalent to computing the same thing, dot product between this transformed data points in H. Okay, so either way, this dot product returns a scalar, and this dot product, of course, I am assuming kernel function as a dot product, returns the scalar, right? So this is the biggest or the very crucial component. Okay. So we are moving this computation of dot product from the Hilbert space or in the higher dimensional future space to the original input space, and we look for a function k that does that. Okay, so we just look for it. Fortunately for polynomial transformation, it is simply right a dot product between the elements and add one, and then whatever the order you want, you put that p here. Okay, and this allows us not to bother about phi. Okay, I don't even care about the relations in phi. Okay, so I don't even want to compute this phi. Okay, because it allows me to do the same thing in the lower dimensional space. Okay, that's where this kernel function is coming in. Of course, you can see the equivalent as you can construct phi of x by expanding this term, and then you can see that you expand this term, just square it, and you end up with a transformation mapping. But in fact, I don't need that. Okay, so here just for illustration to see how things works, we are expanding all these things, and this particular kernel function is equivalent to computing the dot product in this space. Okay, but we don't need to compute that. Okay. Yeah. So things are clear so far, right?
So there will be one more root 2 over here, no? Phi x transpose f1
Maybe I
square.
missed that.
Yes, here will be one more root 2. Instead of root 1, there will be root 2.
So here you mean?
Yes, sir.
Okay, okay. So maybe I missed that. But of course, you expand this equation and arrange the terms, you will end up with some phi of x.
Also, sir, one more doubt. Say, for example, I have a mapping in mind and I want to formulate a kernel from that mapping. Is there a way we can do that?
So you have a mapping in mind,
Yes.
and you want to do the inverse stuff. From phi of x, you compute the respective kernel.
Yes, sir.
That I'm not sure about.
Okay.
I mean, there since the relation exists, it should be possible. That's what I believe.
Yes, sir. It should be really.
As long as it is in a lower dimension, I think we can do that.
Okay.
Okay, so this is the key takeaway. Keep this in mind. Okay, so whatever we compute.
One more doubt, sir. Sir, while calculating this phi of x of transpose, we are converting this x into a polynomial degree of degree 2, correct? So f1 square, f2
Degree
square.
6 now.
Yeah, it is degree 6 now. But why do we need that root 2, sir? F1 and F2 is enough, no, sir? Well, if we are computing.
No, when you write this as a dot product, it is required. That is covered in the lecture. Yes, yes. No
Okay.
changes.
Okay, sir.
Yeah. Okay. Yeah. So shall I move on to the next slide? So we have 3 to 4 more important slides, but ensure that you got all the important things covered so far. I mean, you have no doubts in it.
Sir, so basically, this in whatever input space our data point is, so we are just making use of that space only using kernel, right?
Yeah, that is exactly correct.
Instead of just thinking that we have to transform it and add a new dimension or whatever, so we don't have to do those steps. So
Yeah, we
kernel
don't do this transformation explicitly. Yes.
with these derivations, we don't need to remember this formula is fine with, like understanding that this is the formula to calculate it for kernel or something like that. For kernel.
Remembering the formula, I'm not. I mean, which one you're talking about? Remembering which formula?
Like if we want to the polynomial kernel that we see k colon x1 xi transpose xj plus 1 whole square. So just knowing this formula is fine, or we need to understand how it got derived.
Yeah, I mean, if you remember this formula, that's fine.
Okay.
You can replace 2 with p, and of course in the assignment questions you are being asked to check whether this is a valid kernel, all these things. You can use these relations to validate whether the proposed transformation, of course, for the sake of checking your understanding, we limit to 2 3. We can't even go beyond 3. Okay, that is even difficult. Even going to 4 is not encouraged. 5 is not at all required. So we number of features we never go beyond 2 from the exam perspective, and also for P we never go beyond 4.
Okay.
Okay.
Sir,
Yes.
so can you just go to the first slide, sir? That circle you had, that f1 minus a whole square plus f2 minus b whole square equal to r square. Yes, sir. So
This
for
one.
this, there will be different kernel functions, sir, because there is no square root of 2.
Yeah. I mean, here we are just bothering about phi of x, right? We are not computing anything. We are just doing transformation. But when we compute dot product, right, we bring in
Yes,
the
sir.
square root only when we compute the dot product, ensuring that the coefficient result in 1.
No, sir, if you have to calculate the square root of phi now.
You can add it if you want. It doesn't make any change in the
No, sir,
transformation.
do we need kernel for this? Because this is in 6 dimension.
Yeah, for this transformation, you don't, I mean, here we are not talking about the kernels at all. We don't need kernels. Only when it comes to the computation of this phi of x transpose and phi of x, we need kernels. To avoid this explicit computation, we are looking for kernels.
Yes, sir. If we are doing this computation in this problem.
Yes, for that we need kernel. Yes.
So that will not be the linear kernel.
Why are you saying that will not be a linear kernel? See, what we are doing here is a linear kernel, right? I mean, this dot product is linear, right? Why we say it is linear? Because we say the projected space in itself is a linear, right? So it is going to be a plane. All my transformed points are living in this plane, okay, which is where I have the vector u here, and I'm computing the dot products between these points, which is residing in the linear subspace. So the dot product is linear.
Yes, sir. To compute the dot product, we need kernel function. So how to find the kernel function?
No, so remember we never. I mean, there are two things. One is we are not going to phi of x, and from there we are looking for kernel. Okay, so what we are actually doing is that I define a kernel k. Okay, in the transform in the input space. Like now, let's say I have this kernel, right, on P. So the moment I define this, define this kernel, I can throw away this phi of x. I don't need to care about that, right? But as I think someone asked that if we have this phi, can I compute this k? If that is your question, there is a relation. There must be a relation, but that is not we are doing here.
And sir, in this case, will we think of any error like residue or anything like that?
No, we are not talking about that so far, and we don't need to, because we are first talking about how to compute. I mean, how to project all these points, right? So only if you are able to project, then we can talk about the error.
So through kernel, we are doing that, right? Means that's the solution we found using kernel.
Yeah, that's true. But so far, I haven't talked about that, right? So I am focusing on the aspect that we never do the computation in the transform domain, and we do the computation in the original domain, which is equivalent to the computation carried out in the transform domain. So that is the point I wanted to stress now, and that is what I want each one of you to grasp. Okay. So if you have some confusions in the lectures, I just try to make it clear. Okay, so we have all these things, and remember that this is for a single elements xi and xj from x. Okay, so this is going to be a single number. So I can form a matrix K by doing this computation for all pairs of I comma j in the for all I comma j from x. Okay, so this will give me a kernel matrix. Okay, and yeah, let's move on with this. Again, I want to put a simple example to illustrate the important idea. Okay, so let's say I do a polynomial transformation of degree 10, and I have this data set with 100 samples and 6 features. Okay, and of course I can compute this covariance matrix, which result in of size 6 by 6. But if I apply polynomial transformation 10 here, okay, even for these 6 features, you can see that my xy will have 8008 features. Okay, then I can, if I am computing, okay, if I compute this covariance matrix in the transformer domain, then the dimension of it will be 8008 by 8008. Okay, so if you look at the first row of this covariance matrix, so this is how the computation is done, right?
Sir, how it is coming 8008?
You use that formula of degree 10.
Okay, summation of pth power. That one.
No, not that one. It's p. I don't know. D plus p. Choose D.
Okay, yeah. Okay.
Okay, so what I want to do is I want to compute this C of phi, and I can see the equation for C of phi. But what I claim is that we can't compute this C of phi, and we don't want to. Can we compute K of phi instead? Okay, because C of phi is 8008 by 8008. Can I at least compute K of phi, which will be of size 100 by 100? Okay, which is much less than this 8008 by 8008. Okay. Okay. Can you see the problem here? I can't also compute this K of phi using this transformation, right? So I can use this kernel transformation to compute K of phi, but do you think can we compute this K of phi now?
Sir, why not?
Okay. So what you need, how many elements are there in this K of phi now?
100 cross 100.
Okay, so the size is 100 by 100, right? But my original x of I and x of j, how many, the I and j can vary from 1 to up to which range?
1 to 6.
But if I want to compute x1 and x100, how do I do that?
So when we are
So the range will be from 1 to 100.
Yes, sir. The range will be from 1 to 100.
Why
And,
do you say it is 1 to 100?
because sir, there are 100 number of
points.
data points. Yes, sir.
Mm-hmm.
So for each element in the kernel, we will just we can just compute the upper triangular matrix, and then we can just fill the same thing below because it is going to be the same. So
Okay, I
instead
have
of
x, okay, which is 100 by 6, right? And I am arranging this column like this. We have 100 samples, right? Yeah, let me first display all. What is the problem? See, I had a what is x7? X1 is the first sample, x2. Okay, so I think I made a mistake here, or I might be misinterpreted this. Okay, so anyhow, in the next we are doing the same thing but in a different way. Let's see how things goes here.
Sir, before moving to this
Okay.
8008, this is also, how do you calculate that, sir? Actually, the dimension is 100 into 6. So 600 plus the power. That's no, sir.
Which one you are talking about? 80?
8008.
Okay. This one?
Yes, sir. This 808 using that formula.
Yeah, so we have x5 of size 100 by 8008. So if I want to compute the covariance
No,
of
that 8008 only I'm asking you, sir, how that comes.
I'm using this polynomial transformation of degree 10.
Yes, sir, I understood that. Degree is 10 and 6, and here the original dimension is 100 into 6. So
The
600.
number of features is 6, right? You have to consider about d. D is equal to 6.
Yes,
And
6.
the required transformation of order is 10, right? So it is 16 choose 6. Sorry, 16 choose 10. Can you check that
Okay,
whether you are
okay,
getting
okay.
this one?
Yes, sir. It is the same one. I
Yes, sir,
calculated.
same. Sorry, sir. I misinterpreted. I calculated for 100 into 6. Okay, sir.
Okay. Yeah, so I in fact wanted to take an element from C. Okay, so of course these points are not needed. So what I wanted to convey is that we just map, you can compute K for x, right? Instead of computing c, you can compute k for x, which ensures that here I have k of size 100 by 100, and also in the transform domain k phi will be of size 100 by 100. So we have all the elements here, right? So what we do is we do the same thing, okay? Use the same kernel. We already computed all these things here, okay? So I just wanted to draw correlation, okay? So how we directly move from k to k plus 10, okay? So I can simply put k plus 1 here. I mean, you can write this entire expression as like this. What we are doing is we are adding 1 to all the elements in the matrix. So it is just a matrix, and we are taking a power of it, okay? So which means this k phi is written as a function of k, okay? So that is what we wanted to do. Once we have k, then we can compute the eigenvalues and eigenvectors for k. So instead of taking the root of c, we are taking the root of k in both the domains, okay? Okay, so does this make sense how the computation actually flows?
Yes, sir.
Yes,
Okay,
sir.
so now
Understand well. Sir, I did not understand well.
remember, I want to compute k phi because that is the feasible thing, right? So the dimension is 100 by 100. So to compute k phi, I need to compute all these products, right? Each element in k phi is a product of these transformed data points, right? The
Yeah.
first thing, I don't want to compute transformation for all the data points, okay? So I don't have this. But I want the equivalent representation, okay? So but I want to compute k phi, but not through this product, but instead of using the kernels, okay, which are equivalent in terms of the computation, right? Both gives you the same result. So we have k here, okay? So all the dot product, for example, I have matrix k here, and I have computed k11, right? I could have computed k11 using the data points from the original space. And the first element of k phi will be simply k11 plus 1 whole power 10. So which I would have obtained if I have computed this phi x1. If I compute this phi x1, this will be equivalent to this value.
Okay.
But I don't want to compute this because for the reasons we have seen earlier. But now we made it equivalent. We are this. So all these things are just happens via the original space. We are not doing any. The original space gives the equivalent computation that is happening in the transformed future space. That is the point. That is the key point.
Okay.
Okay. So now we have this k plus 1 by 10, but we can compute eigenvalues and eigenvectors for this, and then we can transform this to c. Okay, so remember this is k phi, and I can compute the eigenvalues and eigenvectors, and I can do this mapping as we have seen earlier. But once again, we face the problems, right? So the thing is like this. We are not able to center this data set because we are not even computing phi of xi, right? So unless we compute the phi of xi, we can't center the data set. And we can, to compensate that, we can center the kernel, okay? That is why we do this kernel centering operation. So you see the reason, right? So we need to compute the eigenvector, okay? So this eigenvector is actually belongs to the covariance matrix of C phi, where we have to use this relation, okay? So I can compute the eigenvector alpha k. Of course, I must have used this phi here, which belongs to which is the eigenvectors of k phi, okay, the kernel matrix of the transform domain. And then I use this transformation matrix, and then I compute this eigenvector, and immediately we can see the problem, right? So the transformation matrix means I need to transform all the points. But we don't want to do that. We don't want to compute phi of xi because of the computational load or computational complexity. Okay, so this prevents us kind of computing the eigenvectors in the transformed domain. But as the rest of the things are discussed in the lecture, that we can anyhow get the projection of these data points onto the eigenvectors of C5 via different route. Okay, so I think once you understand all these things, then this is just 2 steps forward. What we are interested in computing the projection, and if you have made sense of all these notations and what this transformation and what the matrix kernel matrix stands for and why we compute that. So if you have understood this, then these are all just algebraic manipulation. Okay, so eventually we ended up with a simple equation. So I have an eigenvalue of k phi, eigenvector of k phi, and this one is a particular component of the eigenvector, and then I have this kij as well. Okay, of course, various k phi. Okay, so we have these two quantities. So using these two quantities, remember this k is also computed in the original domain, and eigenvector is computed out of this original domain. Okay, so by making use this, we can project. Remember what this equation is. This equation is the transformed data projected on the eigenvector in the transformed space, which is equal to xi transpose wk in the linear PCA. So now my xi is transformed, but we never transform the points, but we want to carry out but I want to project it. Okay, so the projection can happen via this kernel matrix. That's the point. Yeah, Varun.
Sir, so the sigma kij and alpha ki, this we are talking about the kernel matrix of k plus 1 to the power 10, right?
Yes.
Okay.
K phi is k plus 1 to the power 10.
Right. Okay.
So here there is one small typo. I think in the second equation, phi of x I is written, phi of x j should be.
Sorry, it should be j. Yes. Even here, I should have written this as I. Yeah, this is I, and this is j. Okay.
This is second alpha k j.
Sorry, I'm not able to see. Oh, this one. This
Yes,
is
sir.
alpha k. Yeah. Okay, so now you can clearly see that we never go to the transformed space, which means we never transform the original data points to the higher dimension. One is computation perspective, and it also limits our capacity, right? So we want, what if I want to move to the infinite dimensional space? Okay, so then it is impossible to compute this transformation. But this connection, this kernel matrix, alleviates that problem and gives us a way to do the same thing in the original space that could be computed in the transformed space. Okay, so this is a very profound idea.
So one drawback here would be that if we take a small value of n, say if we take a small value of n, and that does not capture 95% of the variance, let's say, information, then because sir, since we don't know the actual values of actual eigen values, so sir, we cannot actually determine n. So we would have to guess n, right?
We don't know the values of, the direction of the eigenvector, but we know the variance captured by these eigenvectors, right? Because the variance is related to the eigenvalue, which is given by the square root of n lambda in the transform domain. So we can compute this variance. If I'm not understood your, so if I understood your question, I think you're talking about that, or your question is something different.
So my question is something different. So we calculate the covariance matrix in the higher dimension. Say theoretically we are able to calculate all that.
Okay.
And we then calculate the eigenvalues on the of that matrix. And then we evaluate
Eigenvalue and eigenvalue and eigenvector. Okay.
and then we try to evaluate how many principal components we will need eventually.
Okay.
That is basically the value of n, right? In this case.
How many principal components? So number of principal components depends on D, right? See, if I okay, so let me take an example. Even if you have a covariance matrix in the original domain X, okay, and which is contained R n by D, then my covariance matrix will be of size D by D, right?
Yes.
So how many eigenvectors are possible here?
D at once.
So it is 1 to D, right?
Yes.
Okay, so does that answer your question?
No, sir. Sir,
No.
so what I'm asking is that how did we choose n? Means like here we have chosen.
So you are choosing K, you are talking about K, number of eigenvectors.
Yes, sir.
So n we are using it for number of samples, small n. Then if you want to prefer how many principal directions I need to choose,
Exactly.
that is what you're going, right?
Yeah, yes.
That is given by the eigenvalue, right? See.
So, sir, basically
we
in
have,
this, if we get a value which is like greater than 95%.
yeah, say for example,
so then
if
we
I
can
have
swap
D,
that those principal components. Right?
so you take a ratio, right, between this. What is the variance captured by a first principal component and how much variance is captured by second principal component, and you sum them up until you get 95%. That's how we proceed, right?
Yes, sir.
But the variance is given by the eigenvalue, not the vector, right?
Yes, sir.
But we have the eigenvalues of C5, right? We don't have the eigenvectors, but we have the eigenvalues.
Okay. Okay. Yes.
Does,
Yes. 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 Okay. 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 Got it. Got it.
okay. Yeah, so kernel centering, I think I needed to talk about that. So, but I would go with this equation, which is as is in the paper, which is quite straightforward to remember than the equation in the lecture. Both are equivalent, but whichever you prefer, you keep that. This is just a kernel centering operation that we typically do. Okay, so that's all about kernel PCA, and I know if you are learning this for the first time, it is going to take some time. Okay, so go through slowly and work out each and individual step and try to make sense of these steps and what they are doing. So if it doesn't make sense, if it is logically correct, leave it until wherever you can make sense of your steps, do that. Okay, so to get the full flow.
So, sir, in this we are not going to consider any error. We won't get any error. Or it is like error free.
No, the error is, so once you project, right, you get the projection back. So once you have that projected values, you could compute the error. Remember, it is very, I mean, in practice, what happens is that even though we claim that all the data points are, absolutely lie in the lower dimensional space, for various reasons, it never happens. So, of course, kernel PCA is a very old trick. There are many advanced algorithms like, linear embeddings and TSNE, so which try to look for such spaces where we can minimize the error. But of course, all they are backed on, reducing this error. We can still compute it. That's what I can say now.
So once, since it is like projection is done, so it acts like normal PCA thing, that how we calculate the error and all. Once it is in the linear this, right? Linear subspace. Means through kernel we are achieving the linear subspace, right?
Yes, that's
Okay.
correct.
Once it is done through that, then we can apply like week 1 concepts to that.
once we done that, what you're saying, I'm not able to get your last point.
Okay, so my point was like our goal was to get the things into a linear space, subspace, right?
That is
Through
correct.
kernel, yeah, through kernel we achieved that.
Mm.
And once since we are doing the projections and everything, so basically we are finding the W like that, right? Eigenvalue and eigenvectors and all, whatever. So then we can conclude in the same way as in week one concepts we had, like finding the residues and those things. Can we do that even here?
Residues, yeah. So that's a good question. So that is where we encounter a problem, right? So unless we have this eigenvector wk, then projecting, I mean, reconstructing is prohibited. I mean, unless I have these eigen directions, right? I know the variance captured along a particular direction, but I'm not able to recover this, right? So that is the problem. So in original PCA, right? I mean, in the linear PCA, what we do, I mean, even in the simple case, let's say the data points are spread like this, and then I have this eigen directions that captures where the maximum variance is. Okay, so projection is I'm projecting this point onto this eigen vector or along the eigen direction. Okay, so for reconstruction, what do I need?
So reconstruction, I think
The projection can happen. Okay, that's via the kernel K.
representative and coefficient we will require, right? For
Yeah.
reconstruction.
Yes. So the representative is the eigenvector, right?
Mm-hmm.
So that's where the problem is. So typically, of course, from the application standpoint of view, kernel PCA, I mean, so where you don't need this reconstruction, right? So only what you need is this separation. So kernel PCA is applied in that case, like in SVM and also in visualizing stuffs. I mean, visualizing the data points in the higher dimension by projecting it back to the lower dimensional subspace where the projection is required.
Okay. Here we cannot think of reconstructing the data points, right?
Yeah, yeah.
Kernel we cannot think of doing that. Okay.
Because we're not
Yes.
finding W, right? Eigenvector.
Yeah, that's
So,
true. Yes.
so sir, when we are bringing the dimension of the data down, we just take the first three principal components and then we visualize. Other than that, we cannot do anything.
Yeah, that's what I'm saying. So typically you can use that to visualize the higher dimensional data set in the lower dimensional space. I mean, you have original X, which is really high, let's say in 1000 dimension, but you want to visualize this. Instead of applying linear PCA, you can apply this nonlinear PCAs like kernel PCA and TSNE to see how things are related in the higher dimension. That's all.
So what are the any real time example that we can relate for
Real
kernel?
time?
Real time, like where it is applied these days for
Yeah,
kernel.
one is for projection, visualizing the higher dimensional data set. Of course, there are alternatives, but you
It's
can see some.
application, sir. I'm asking about application where it is applied these days.
In
Real
SVM,
time.
support vector machines, that is one thing that you come across in the subsequent weeks.
Okay.
So this will be just used to see if there are relations in higher dimension. Like say, for example, if the data belongs to 4 dimension and then we don't know any relation between them. So we can just apply kernel PC and somehow we fit it inside a higher dimension. And then we come back. We see that, okay, there is a relation.
Yeah, that's true.
Relation. Then that would
Even
be
in the
very
clustering, people do that. You have data in higher dimension and you don't know, is there a group in the data set, right? So we
yes.
have thousands of samples, but I don't know how much samples are close to, I mean, is there a group? I want to, if I want to visualize that, I can project the 1000 dimensional data set to 3 dimension. Again, that's a projection. Yes.
So that could help them decide the value of k maybe because they don't know how many k to start with.
Yeah, that's a case a hyperparameter. So this is a good, what do you say? Instead of going with heuristics, maybe we can, of course, this is also heuristics, but it's kind of a better principled way.
Sir, so after we do the kernel PCA, we store the projected values or the dot products on different eigenvectors. That's it.
Yeah.
We
For
cannot.
projection, we just do that.
So we cannot store the exact reconstruction of the point. We just store the dot products.
Yes. For reconstruction, we need eigenvectors. That is, we can't compute that. I'm not sure. Is there? I mean, maybe in the literature, people might have attempted to reconstruct it via some approximations, but I'm not aware of that. Whether it is possible to get back the eigenvectors.
Sir, also the kernel PCA has a lot, all applications, sir. We can use it for clustering, for classification, also for representation learning, right?
Yes. But I'm not sure whether people here are comfortable with those. I mean, at least aware of those topics, clustering and all this classification. Maybe in machine learning foundation, you might have studied about regression and classification. Maybe in the week 3-4, I think they are covering clustering.
No, so clustering was covered in the last few, where we see the EM model. So we just start with that, and then we start to approximate the normals, and then we come to a chicken and egg problem and that like that.
Okay. So then what is covered in week 3 then? Let me see.
So week 3 only Hermitian matrices and symmetries and all that.
Okay. No, in machine learning techniques course, not in machine learning
Oh,
foundation.
okay. Oh, okay. Sorry.
Okay. So yeah, I hope now you get some picture of what kernel PCA is doing and why we do all these stuffs. Why we running around? Not running around. In fact, it's a very impressive idea. You can refer to a book called Kernel Methods. Written by the authors who developed all these things over some 30 to 35 years of time. So that gives you a lot of insights and also gives you different types of algorithms. So if you are interested in this approach, you can take a look at them. Yeah, Prashant, you raised your hands.
Sir, could you please go back to that circles of it? Initial that it was in R2, 2 dimension.
Okay, I can draw it here, right? Or do I need to go
Yes,
back?
sir, I have some doubt.
Okay, let's say I have circles. I am approximately drawing it. Okay.
So suppose we want to represent these points, sir. So if we apply the standard PCA, we'll need 2 eigenvectors. Right?
That's correct.
So we need to store the 2 eigenvectors plus the 2 coefficients for each data point.
That's correct.
So suppose we do kernel PCA and project these points into R6.
Okay.
And suppose they lie in R5 or R4 in R6 in a linear subspace in R6.
The linear subspace will be R2 only. Okay.
Okay. It cannot be in R3 or R4.
No, so I mean, when I say R2, it is like in 3 dimension, right? When I say R2 contained in R3, I have multiple directions, right? Either R2 could be this plane, or this plane, or this plane. All these are R2 plane, right? So that's what I mean by R2.
So we still need 2 eigenvectors, sir, because we still have a plane. So instead of
We
doing
need eigenvectors, yes.
So instead of doing this in the original R2 space itself, we could have kept 2 vectors, right? As representatives.
No, that will not match because in the original R2 we have the eigenvectors of C, right? Eigenvectors that is coming from C, but in the transformer space the eigenvectors are coming from C5, right?
Sure, what, sir?
So if you want to reserve the eigenvectors of C in place of C5, that we can't do that, right? One thing, we are not computing C5, and the other thing is that these two are not related, right?
Yes, sir. So even if you project it to higher dimension R6, it will be in a linear subspace in a plane only, sir, R2.
Yeah, that is correct.
So we need two eigenvectors to represent it. So
Yeah.
instead of that, in the original R2 space itself, we could have kept two eigenvectors. And
No, the problem is the variance. See, it is like, let's say, even without going for C, I use these two vectors. Okay, that is 1 0 and 0 1. Okay, so this is an eigenvector of, I mean, the default standard canonical vector that represent these points. So even if I compute eigenvectors, I end up with vectors like this. Okay, which means it is not capturing the variance in the sense there is no particular principal direction where the data varies more than the other. So the data varies along all the direction equally. So that is why we are not using this. I mean, computing the eigenvalues and eigenvectors for these data points doesn't do the job. It doesn't compress the data points for this particular setting. That's why we are not using the original eigenvectors. So if I have understood your question correctly, I think this is the answer. Or did I understand your question correctly?
So if we, okay, when we do polynomial transformation, so we are projecting to higher dimension space. So still we will be, the data will be constrained into the original space you are saying, right? In a higher dimension. Okay.
Yes.
So that means only few features of polynomial transformation will be useful, but we can't find it initially without doing this, right? We still need to project it to the all the transformation for complete transformation.
Your voice is breaking. As I lost you for.
So sorry, I will change my mic. Sorry. I'll call you later.
Sir, so in kernel PCA, we are not doing any compression, right?
Yes, we are doing the projection. Compression, we are not doing that. Yes. So if you want to compress, you need to store the eigenvectors, which we can't compute that.
Sir, even if we store it, it will not be compression, sir. It will have more numbers.
Yes, that's
So
correct.
it is not we are actually increasing it.
Yes, that's true. Even the dimension of the eigenvector will be much higher.
So that will be higher than ND, right?
N and capital D. Sorry, small d. Yes.
Yes, sir.
So one more thing, separate from what you are discussing, centering in the higher dimension in the transform space. Sir was saying something about that. I was not able to understand that. Could you please talk about that?
Centering in the transform space. Yeah. So let me tell you the idea. So we have X. It's a matrix, data set matrix, and then we have this transformed X, right? So
Yes.
typically when we compute the covariance matrix, we do centering of the data set. We compute X minus mu. Okay.
Yeah.
Remember, mu is a vector. X is a matrix. So when we want to compute the covariance matrix in the transform domain, again we want to center this. Hey, give
Yes.
me a second. Yeah, I am getting a call from the prof. Yeah. So we want to center this, right?
Yes, sir.
But anyhow, we are not computing this. We never computed this, and we don't want to, right? So
Yes.
then how do you compensate this centering operation? So you can compensate this by seeing how do you compute the elements of the each element of this covariance matrix in C phi is computed as phi of xi minus mu, say, and then phi of xj minus mu, right?
Yes, sir.
Then you take this, you generalize this, so you see how things works here, right? So you take this transpose and then phi of a minus mu. Okay, so it's a inner product, right? So he has written, he expanded this. Okay, so typically it will end up in phi of xi transpose into phi of xj minus mu times all these quantities will come. So you can see that, right? I think also plus some constant comes. You just do this, right?
Yes, sir.
So so if I have done this, meaning that I
So
have
this would
only this, I
mean
have,
that we are, sorry, sir. This would mean that phi will always be linear map. It will never be a non-linear map for anything, for any kernel, right? Just for clarity.
no, we say the mapping is non-linear, but the place where the final mapper data points lie is in the linear subspace. It is like because we can't say the mapping is linear, right? Because we have this square term. This is a polynomial mapping, in fact. So the mapping is non-linear map, but the data points after where the data points lies after this mapping is in the linear subspace. That's the point.
Yes. Okay.
Okay, so this will result in k, and similarly you can express these quantities, the rest of the quantities, as function of k, and in addition to this ki, sorry, k1. You just work it out, you see it's just an algebraic step.
Okay.
Sir, so this higher power, whatever terms we have with the higher power, will have definitely is going to have the highest eigenvalues, right? Because that is going to spread out.
Which, sorry,
No, if
whatever.
suppose if we have a term with the x1 cube.
Okay.
Okay, the x1 cube going to be a higher number comparing to all x1 or x1 square or x1 into x1 x2. So this is going to be definitely spread out when we project it, right?
I'm not sure whether we can climb like that. The spread out. I mean,
So
the
suppose
numbers will definitely
the
high.
numbers will be numbers will be high. Okay, when the numbers will be high, that is going to be the principal direction, right? Because
No,
otherwise the error, if it is any other direction, the error will be very high.
Means I think, sir, what he is trying to say is that after transformation, what I say is that variance will decrease with respect to a few components, and variance might increase with respect to other components. Because if we take f1 square, then that means if they are on different sides in the original space, then they will come on the same side in the space in the final space. So which will basically decrease the variance. But if we are just scaling them linearly, then it will basically increase the variance.
Okay, for example, if you
yeah,
take
yeah.
the data point 1, 2, 3, okay, 1, 2, 3, 4, okay. So when 2 becomes a cube, then it is 8, then 27. It goes with the third power, right? So the
Yeah.
data is going to in that particular axis, okay, whatever dimension that is, in that axis, the data going to be far away, the points.
Yeah.
Okay, okay. Since the points is far away, then that means the principal direction tend to be in that direction.
That's
Because
the.
otherwise, if it is in any other direction, the error will be.
Okay, so I get your point because in higher the power, then the distance between the points are going to be larger in that direction. But will that be a principal direction? I mean, intuitively we can argue like that, but unless we prove it, we can't say that. I mean, many things that make sense in the intuitive, in an intuitive way may not be true when we prove it. So we might imagine that, but I'm not sure whether that will be a, that will holds true.
Okay.
Maybe we may ask this to Arun sir.
Okay, sir.
Sir, could you please explain that centered kernel matrix, sir? This formula which you have written on the screen, I understood that dot product. So.
Here, yeah. So this one.
Yeah, sir.
It's just a next step of what Sir has written. Sir has written for each elements of this K, right? Kij. So if you closely look at, to draw the similarities between the lecture here, what the difference is that he has expressed the same quantity. So here, I think he has written this as some theta, and then some 1 j and theta I, something like, and he expressed theta I as function of the elements in K, right? Ij, all these things, right? So essentially what we are doing is, I mean, this is a 1 by 1 matrix, all these things, sorry, not 1 by 1, n by n matrix with all elements 1, and we have K here that we already computed, K5, okay. And then what this matrix product does, it simply sums the elements along the columns, right? Is that your question, or you are asking how we come to this particular representation?
Yes, sir. So K is a vector here.
No, K is a matrix, the kernel matrix.
Oh, okay.
And one is also a matrix. One is this matrix, np dot ones. I mean, it is all ones. The elements are all ones, and we multiply this with 1 by n. So these are all matrix. So we center the kernel, okay, which is a matrix in itself, using the existing kernel as a function of the existing kernel. Okay, so the derivation is in the paper. I mean, not a derivation, so it is just 2 steps, but you may look at this paper. You just type it, this name, you will get this in the Google.
Sir, where can I find these slides?
A slide, I will share it in the discourse. A link to the slide will be shared in the discourse. So I need to fix the typos. So I fix it and share it in the discourse. Okay. So if you find any typos, please let me know. I fix it after I share this deck in this discourse. Okay.
Sir, I joined late. Is Gaussian transformation is discussed already?
Sorry, which transformation?
Gaussian, then to transformation to the infinite space, which
No,
I
I haven't discussed that radial basis function. You mean?
Yes.
No, I didn't discuss that. What is your question on that?
I'm not able to understand that one. How actually that is working?
Working. Okay, so it's not expected to. I mean, you are not expected to derive that, but the idea is simple. We have a polynomial transformation, right? So polynomial transformation means the degree can vary 1 to infinite in principle, right? So we claim that going for higher degree is good, but what is the limit to the highest degree? So the limit is infinite, right? So going to the infinite, we say going to the infinite degree polynomial is best, but how can we go to the infinite polynomial? So the idea is they do something like they take all the polynomial transformations. Okay, so all polynomial transformation of degree I. So I am just putting, maybe I can put here of the data set, okay, and take the linear combination of it. Okay, let's say I is equal to 1 to infinite. Okay, so which means I am applying the polynomial transformation and I mean linearly combining infinite polynomials. Okay, so I transform the data in all order polynomial. Of course, we know we can't do this. Can we come up with an idea, okay, where I have these infinite polynomials? So can you think of a series which relates the infinite polynomial with some known function? So I have a polynomial of infinite order. I sum them up, I end up with a function.
Taylor series.
Yeah, so Taylor series, and we have a representation, right? We have many ways, and exponential, you can see that exponential is also expressed as sum of infinite polynomials, right? So again, I'm just giving you an intuition, not the exact step. Okay.
So x divided by 1 factorial plus x squared divided by 2 factorial, like that?
Yeah, that is right. So I'm just putting that as constant here. So the idea is I have infinite polynomials, okay, and I want to compute them, but we know computationally that not feasible, and I want the equivalent way here, right? Anyhow, we are not going to compute this, so I want an equivalent computation happening in the original domain. That's where this E comes in. Okay, then the rest of the things, of course, all these norms, x minus, I think.
Sir, could you
Xi
show the
is with
phi, means like the linear map phi for radial function?
sorry, you mean linear map of what?
Of the radial function of the
Yeah, so in
of
fact,
Gaussian kernel.
yeah. So I recommend you to refer to this book, Christopher Bishop, Pattern Recognition and Machine Learning. So there he can show you that. So if I remember rightly, I'm not able to recall that, but there is a figure, okay, where we can show this. So within the order -1 to +1, we limit the range to -1 to +1, and you draw all the polynomials order 1, order 2, and then order 3, something like this. So okay, so this is the feature space, okay, where I make use of all this polynomial transformation. Of course, this is for one dimension, and then the equivalent computation will look like something like this. The kernel function that does the same job look like this.
Okay.
Yeah, but to know more, you may refer to this. I think Bishop is a very good
Why it is
resource.
called radial, sir?
I'm not sure why it is called radial. I know why it is called as, I mean, people have different terms based on their background. So even the kernel is called as potential function in 1960s. I'm still not sure why it is called as radial function. But I have come across many articles where they give you the reasons, but I'm not remembering
Sir,
that now.
kernel also said the name kernel doesn't make sense over here because kernel basically says the zeros means the
Sorry?
zeros before transformation. Means kernel space from what I remember in maths 2 and
No, in linear algebra, yeah, the definition differs across the domains. Of course, in the kernel, from the subspace of a matrix, you can see what the null space, all these things, and null space they call it as kernel space. But this is where, even if I ask you why people call it as an eigen, why it is called
so
as
eigen
eigenvector.
means German eigen means own. So that is
Yes.
why so eigen
Yeah.
means its own vectors before and after transformation.
Yeah. So
It
that's
doesn't change
people
its
should.
directions.
Yeah. So why the terminology comes, because the mathematicians of most of the mathematicians, are from German, so they use the terms there, right? So unless you go back and look at the history, we may not know why it is called the way it is called. That's why for radial basis function also they have different reasons, but I'm not remembering that. but it is always good to look at the.
So that means this radial transformation, this will be the best, right? There is nothing best we can do more than this, right?
Yeah, because we already are in infinite domain, so that is the best. But radial, that's the how it relates with the radial. That's I'm not sure. Is that something related with the radius? Is a polynomial and also radius?
No. What I mean to ask, sir. So if this is the best, okay, do we need to attempt any other polynomial at all? Because if we have an efficient way of doing this, then why do we need to even try for any lower degree polynomial?
No, in SVM people do this. I mean, it is not in the literature. We have all this to see. Even we have a dedicated research domain for polynomial classifiers where we do all this polynomial transformation, all these things. Still, there is a research happening. So for each of these categories, we have advantages and drawbacks based on the domain. Okay, so in a particular domain, we may not be able to collect even 3 to 4 samples. So how do we address that? So it depends on, no matter which method you take, all the methods have their advantages and disadvantages. So it is up to us, right? Whether we need to.
The Gaussian kernel will basically fit very well with the data, but it means like very highly overfit. I feel.
Yeah, that is true.
It can be only.
But we use that. No. If we have this overfitting problem, we can apply the regularization. But yes, those things are inevitable even in deep learning. Still, we face this problem of overfitting. I mean, the overfitting is everywhere.
Okay.
Because unless we know the distribution of the data points, we can never come up with an algorithm that never overfits to the training data.
So, okay, once we do with the radial, then is there any way we can find out which degree polynomial is actually contributing the highest principal component?
I'm
then
not
we
sure
can
about
convert that. Okay.
So now I'm almost into the deep learning. So for the past 4 years, I'm mostly applying deep learning algorithms and all the advanced deep learning algorithms. It's like I almost forgot the things I studied about these kernel methods. Except
that is completely different, sir. The deep learning, it's not using any of this theory.
No. Deep learning is far from these kernel methods.
Okay.
So these methods were popular back in 1995 to 2010. People were putting a lot of efforts on improving the support vector machine classifier for multiple classes by coming up with different ideas. But once the deep learning pitched in, everybody forgot about this SVM and all this stuff. Especially for the problems where the scale is really important. Yeah, Deepa, please go ahead as you are trying to.
Yes, sir. Sorry to interrupt, sir. Actually, may I know, sir, what type of questions are we expecting from this week, sir? Because, while converting, transforming kernel and kernel PCA, really it's a lot of confusion. So I can't guess how the questions will be. So can you please tell us, sir, what type of questions or what kind of questions do we may expect?
I mean, for now, it's not, we are not kind of expecting you to remember all these things. You should have a basic understanding about these transformations. That's all.
Yes, sir. I have the basic understanding, sir. Now it's very much clear. But while calculating, especially with the root n lambda, wk is equal to alpha k by root n lambda k. So, sir, there we have to calculate eigenvector of the matrix k.
Yeah. We are not going to ask you such computation in the exam. We may ask you whether is this a proper, let's say for example, I'm telling you, these are all the kind of eigenvectors of, we give you the eigenvectors, eigenvectors of k, and then also eigenvalue, and we may ask you to transform this to the at least compute one eigenvector of C using these given data. So you have to use the N formula, not the entire derivation stuff.
Entire things. Okay, sir. Okay. I have the basic idea. Okay, sir. Thank you.
So that's also one of my problem, because I'm not able to remember any of this. I understand when in the lecture, but is there any way I can parallelly do coding without not much intense coding, just to understand how this transformation is happening? Is there any easier way? Which tool I should
are you
use?
comfortable with NumPy?
Yeah, yeah.
Yeah, then you can simply write. See, I have written the collab here.
Okay.
Right. So I just use these three libraries. Okay, so even I generate the data points on my own, just using some NumPy, and then you do this stuff, add some noise and spread this, and
Okay.
then you do zero centering. That's all.
Okay.
And
So
I
can
am
you share
computing.
this, sir?
Yeah, I have given you a week time to do it on your own. Then I will
Okay.
share it
Okay.
in the collab.
Okay.
See, I'm
Okay.
just highlighting this. Computing covariance is just writing this product, right? Then projection. So these are all not tough. Just because the reason why I'm telling you is that the moment you write on your own, you look for a lot of details, and you learn how to put things together. That is why I am just giving you a week's time. Anyhow, I will share it in a week's time.
Okay. Because I think understanding the concept is more important than trying to figure out how to code it right at the moment.
Yeah. So this, I mean, in both the ways, either by writing code, you can ensure that you have understood the concept correctly, at least to some extent.
Okay. Yeah, I
But
will try, sir.
but I would always encourage make yourself comfortable with these mathematical operations, how to logically manipulate things, because that is how we give some sort of guarantees, but not by codes.
Sir, will there be any tutorial on coding, sir?
I think there will be a
Basic
separate
introduction of
workshop.
NumPy and its
Yeah.
functions.
So I mean, typically Karthik conduct an workshop at the end of the course where he illustrates how to write all the algorithms that you have learned in the subject in a piece of converting the algorithms into code using Python. So they do this at the end of the course. I hope, I'm not sure. I asked Karthik whether the videos are available on the YouTube. If it is available, I share it in the discourse, so you can take a look at as and
Yeah,
when
that will
you
be very
study it.
helpful, sir.
Yeah, yeah. I ask him and see whether it is there.
Sir, also
Okay.
one small doubt, sir. In simple PCA,
Okay.
so we are projecting the values on top k eigenvectors, sir. So, and we want to find, if we want to find the residue,
Hmm.
then it is for a particular data point. Then we should take the norm square or norm as the answer, sir. So, in graded assignment, they asked residue.
How we define the residue in the lecture? So
So it
residue
is
is
xi minus xi transpose wi.
okay. So norm is in fact the distance between the points. I mean, you have a reconstructed point and then the original point, and you are computing the length. So for that, you have to use the norm. But norm square
Yes,
is
sir.
it
Should we
possible?
give norm square as the answer or norm, sir?
I think both are just you know
So the
No, no.
numerical
If it
value
is
will
no
be.
no
norm, if it is norm, that the both plus and minus will cancel out, right? Then we will. So I
no
think
even
norm.
if it is just norm, right? So norm is square root of xx transpose, right? So it is always going to be positive.
Yes, sir. But I'm asking just for one data point, sir. So in graded assignment one, they
Okay.
asked
So I
the
look
rest.
at the assignment question, then I haven't taken a look at the assignment questions. You maybe you create a thread in the discourse and then I answer it there. Okay, Prashant.
Yes, sir. It is in question number 5.
Okay, so I will take a look at that. Okay, thanks for joining the session. I think about 9 people are remaining. That's great.
Thank you, sir.
Thank you, sir.
Yes.
Thank you, sir.
So
Yeah.
one thing,
Thank you, sir.
since I haven't watched all the lectures of week two. Like, I'm still learning this kernel PCA. I still have doubts about it. So since I'm learning it, can I create a thread on Discourse if I have any doubts today or while doing this? So you could answer them if possible.
Yeah, yeah. Please do post it in the discourse and tag us. If you tag us, we receive a notification quickly, and then whenever we get a time, we answer the
Okay, sir.
questions.
And so also one thing, are our remedial sessions started on not? I don't know about them. Means I haven't received a communications after I filled the form for these
Okay.
sessions.
No, I'm not sure whether remedial. 1 second. There are some sessions being handled by TAs.
Yes, sir.
You,
We were told that TA sessions are actually different than remedial sessions. So, remedial sessions are like small groups of students that are learning together, and the people who are managing that particular space is actually people who have already done this particular course and have scored really well. So they will be guiding us to if any doubts or nuances we have about any topic.
okay, okay. So
It's
let me
already
ask:
started. Yesterday there was a session.
is that a
Oh,
remedial session?
Yeah, there
no,
was
no.
a yeah.
There was, I guess this was a TA session, not a remedial session.
No, remedial session yesterday. Are you already added into the Google Space? Can you check your space maybe?
Yeah, I checked my space today itself. I was not added into any space.
Okay, then you need to. I think I'll give you one name. So the coordinator. 1 second. Let me just open my space.